risk finding. So always read the small print and just don't believe anything. It's outrageous. This is a very common, the Daily Express again. It's pretty reliable, the Daily Express. You can always find rubbish. If you want mathematical nonsense, go for the Daily Express. So this is daily fry-up boosts cancer risk by 20%. So this is bacon roll, or something like that, a few rashers of bacon. They say increase the risk of pancreatic cancer by almost a fifth. Okay, so should we be frightened by that or not? How can we take that apart? There's one of these relative risks that makes things look bigger. And one of the tricks, if you ever see a relative risk, this increases your risk by something, to translate it to an absolute risk. What does it actually mean in terms of absolute numbers? Well, what it means, it turns out, if you go on to, you have to do the research, the newspapers aren't going to tell you, there's about a 1 in 80 chance that any of us will get pancreatic cancer during our lifetime. Very sad, there's a nasty cancer as well. So there's about a 1 in 80 chance that you will get pancreatic cancer. Now what this means is that 400 people not eating a bacon sandwich each day, 4 of them, no, hang on, I got this wrong. Oh, it's 1 in 100 chance. Have I got the sums right here? 400 people not eating a bacon sandwich goes up, oh, hang on, goes up to 5 if they eat a bacon sandwich every day. That's 25% extra. It should be 5 going up to 6. Yeah, exactly. Yeah, let me just pop it away. Yeah, no. He looks like the sort he'd be smoking, isn't he? Yeah, okay. Well, okay. This again shows you the care you need. I've got the sums wrong here. This should be 5 going up to 6. Okay. So pretend that not eating a bacon sandwich, 5 of them, 1 in 80 will get pancreatic cancer. But if they do, all of these people eat a bacon sandwich every day of their life. Imagine this. Thought of it, it's absolutely sickening. You would get 1 extra bit of pancreatic cancer. Now, if you do the sums right, this puts again in perspective. Again, I'm not recommending, that's a reason to bacon sandwich, but anyway, this puts the thing in perspective about what the absolute risk is. Okay. Now, so one of the things that I get asked to, of course, is, with all these diseases and horrible things we're all going to get at some point or other if we live long enough, and whether we live to 100 or not. Is this all just luck? I'd like to now go on to what is luck? What is chance? What is it? It's actually really tricky. Is it just people say, "Oh, I had bad luck. He got this disease. All bad luck." Well, this is just luck. And what's very interesting, Richard Dodd is amazingly dead now. He's amazingly eminent. He lived for ages, about 90 something. Amazingly eminent man who essentially discovered the connection between smoking and lung cancer. He really discovered with some others that smoking caused lung cancer. So enormously sort of serious. And yet he says that if you get cancer, it's bad luck. He's a wonderful quote. He just said, whether an exposed subject, whether an exposed subject does not develop a cancer is largely a matter of luck. Bad luck if the several necessary changes all occur in the same stem cell, and there are several thousand such cells at risk. Good luck if they don't. Personally, I find it makes good sense, but many people apparently do not. So what he's saying is that all these sort of cell divisions and the mutations that could cause cancer and things like that, really we can just think of it as chance, as luck. And if things happen to line up the wrong way, you get a disease, or you don't. Now, you can change your degree of luck, I suppose, by the way you live and what you do, but in the end, it's just luck. And so what this means is that some people will puff away and smoke and eat huge steaks and live till they're 95. It'll happen. And other people will live this lovely life of very frugal and being very sensible, vegetables and all that sort of stuff, and die of something horrible quite young. Not everybody, it's all on averages. It's huge variability, huge range of young. Okay, so let's go back to coincidences. This is, again, people be fascinated by luck and coincidence, and of course it's largely come up through gambling, what people feel about gambling. So I'd like to try a little game. I haven't done this before, so I'm going to try a little experiment to see what people feel. This is the game of coincidence, and it goes back to what they used to play in the 1700s. And everyone puts in equal stakes. So you think of you, I could play it. Play with this front row. So we all put in a pound, something like that. You put in a pound, and I put in a pound. And I'm the banker. And what the banker then does is shuffle the cards and then put them out in turn. And if, for example, he's got 13 cards, he would say, as he put them out, 1, 2, 3, 4, 5. And if he gets a match between the number he says and the card that appears, the banker wins. If he gets all the way through, the banker loses. And in 1708, they sold it for 13 cards. So let's have a little, see how it would work, say, just for 4 cards. So if I said 4 cards, I shuffled them up, and then, is that going to show? Yeah, okay. So I'm going to shuffle them up and do this. So the game is, with 4 cards, you just say, ace, 2, 3, 4, and I've lost. That wasn't very good. Okay, let's do it again. Banker again. Now, what's your intuition? Is the game in favour of the banker or the game in favour of the person putting on the bet? Who thinks that the advantage is to me, the person who's shouting out the numbers? Who thinks it's in my favour?
With 13 cards?
No, with 4 to start. With 4 to start. Yeah, who thinks it's in favour of you putting on the bet? Yeah, okay. Let's try again. 1, ace, 2, 3, 4. Lost again. Dear, oh dear, oh dear. This isn't illustrating the trick very well. Ace, 2, 3, 4. Lost again. The mathematics shows that it's in my favour. Ace, got one last. Yeah, exactly. Okay, now, trying to solve this problem was a classic thing that people started to get involved with. For example, Euler in 1751 did it for 4 cards. So what he did was work out, for 4 cards, all the possible orders in which the thing could come out. There's 24 of them. 4 times 3 times 3 times 5. 4 factorial ways to do it. And then looked at how many of them would win. How many the banker would win, where there's a match. For example, all these where the 1 came out first, he would win immediately. And then he would win that one because the 4th came the 4th. And he counted up how many. There's one where the banker loses, another where the banker loses, 2, 4, 1, 3, 2, 1, 4, 3, and all these. And it works out that only 9 in 24, that's 0.375 chance the bank loses. So it's in my favour, 62.5%, 5/8 chance that I would win. I was a bit unlucky to lose 3 in a row, to be honest. But if I carried on, I'd have made money. Okay, so that's to do with 4, 0.375. Now, what do you think it would be if I put 13 in this? The game was called Trades, French for 13. So that's 13, so this is all the spades now. What do you think that probably, with 4 it was in my favour. With 13, what's your intuition? Is it in the bank's, who thinks it's in the bank's favour? 13. Who thinks it's about 50-50? And who thinks it's against the bank? It's in your favour. Yeah, okay, it's interesting. We're all to split between people. Okay, let's just try, because it's only one go, so it doesn't really illustrate. But I go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Missed, lost. Okay, I'm not going to keep on doing this. But I'm going to do one more. I'm going to do one more just to show, because actually it's in the bank's favour. Ace, 2, 3, 4. 4, got it. Okay. Now, it turns out then, and then you can go up to 52. For 52, this is a good game to play with people, if you might be able to make some money off them. Oh, but don't gamble. Don't gamble. But if you must, you could take some, I've got 52 cards, and I'm going to go through hearts, clubs, diamonds, spades, and just say the numbers in turn. So I can go, say for hearts, I'm going to go ace, 2, 3, 4, 5, 6. Got it. And I've won it. So you can all play that one. So, and the interesting, so that's a good game, and it turns out that, rather remarkably, from 5 onwards, this is 0.375. From now on, it's always a 37% chance that you will win, and a 63% chance that the bank will win. No matter how many cards you're playing, it's always 63% chance the bank will win. From 5 onwards, it's quite extraordinary. It's also called the hat check problem. It's a lovely idea. It's exactly the same as the hat check, which perhaps may be easier to understand. You've got n men who go to the opera, men like this, and they all hand in their top hats to a ticket to the lady at the counter, who doesn't bother, he just puts them in a heap. Doesn't bother putting a ticket on them. And when the men come back, she just hands the hats back at random. What's the probability Pn that nobody gets their own hat? And if you see, it's exactly the same as the cards with n cards. That's what the hat check problem. It's quite an easier way to remember it. To remember all these pile of hats. What's the chance that nobody is going to get their own hat? And again, that's the chance of no matches, which is the chance of no matches is 37%. Okay, where does that come from? Now, I actually got this off. It wasn't Wikipedia. It was one of the Proofpedias and things. And I'm not going to do the maths a bit. Partly it's quite tricky. I'm sure there might be experts about derangements. It's permutations. You'll have done permutations. The number of ways you can shuffle things up is n factorial. Derangements are particular permutations in which nothing stays in its correct order, in the original order. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You shuffle up the numbers, but nothing must stay where it was. So it really is a derangement. No number stays where it was. And it turns out the number of derangements is n factorial, shrunk by this factor. Now what's curious is 1 minus 1 over 1 factorial, plus 1 over 2 factorial, minus 1 over 3 factorial, plus 1 over 4 factorial. That's extraordinary. And Euler found that in 1700s. So that means that the probability of getting, of everyone getting the wrong hat and no matches is this number. And this number converges incredibly quickly to 0.37. And clever people who have done the expansion for e to the x will recognize that this is essentially e to the minus 1 to a limited number of terms. So what this means is that if this is the number of hats or cards, this is the factorial. The probability there are no matches, we did 0.375, converges to 0.368 incredibly quickly. So the probability of matches there. Now, so it's a lovely thing that people were doing 300 years ago, but I still think is a nice example of something that's very easy to explain, yet really quite tricky to do, and not intuitive at all. In fact, it doesn't matter how many cards there are. I find it not very intuitive. Another way to view it is to think that you've got n cards, hats, each is probably 1 over n of a match, so the expected number of matches is 1. And roughly, you can think of this as the Poisson distribution, and the probability of a Poisson variable is equal to 0 is e to the minus t, which is 1 over e to the minus 1. So for some of you that might be familiar, others it doesn't matter at all. Okay, so what is luck, chance, randomness, chaos? Yeah, anyway, it's a little burst of philosophy, because this is very controversial. Does chance exist? You know, is everything? Are we all fated? Is it such a thing as fortune? Is it all predetermined? We just don't know what happened. Now, it's very controversial. My personal opinion is luck, chance, randomness is the name we give to when we just don't know what's going to happen. When we've exhausted all our knowledge, and when we've exhausted all we currently know about what might happen, is what's left over. So it's a label we apply. That's my personal opinion. People, you ask somebody, you'll get a different opinion. There's no correct scientific conclusion about this. In fact, I think I would disagree with whatever anybody said. I would immediately just disagree with it on principle. But you do know that in the quantum world, there's genuine unpredictability, Heisenberg's uncertainty principle, there's genuine randomness in the quantum world. But in the non-quantum world, the world we live in, the atomic world with gases and things like that, you could say that this is a physically determined system. It's just so complex. In some situations, the dependency is chaotic, which means that essentially things are unpredictable. Whether it's actual genuine chance, I think is almost irrelevant. It's still unpredictable. So it's a big philosophical area which is not established at all. The final thing, though, is that if you put numbers on chance, actual probability, which is a number, what this means is that they inevitably require judgments. I personally believe probability does not exist out there in the universe. It's in there, and it's numbers we construct on the basis that we know. Okay, so that's let's just go on to other ways of communicating probability. And here's me again. I've got, I'm 58. I've got about a 12% chance of a heart attack or stroke in the next 10 years. More if I eat all that meat, but I'm not going to, and so it's about 12% chance. If I took tablets every day, statins, I could reduce this risk by about 33%. So you notice this immediately. We've got an absolute risk here, and this is a relative risk. This is a relative reduction. It's reducing it by a third. We know, from what I've said, is that that sort of language makes things maybe more important than they really are. So the thing to spot, whenever you see a newspaper reporting a percentage reduction, treat it with suspicion. Because what this means is that for 100 people like me, in the next 10 years, 12 of them, the red and the yellow ones, will have a heart attack or stroke, are likely to have a heart attack, expected to have a heart attack or stroke by the time they're 68. So I'm 58. By the time they're 68, these will have, they may survive, they'll have a heart attack or stroke. If all of these people took the tablets every day, the statin every day, it would prevent those four. So that's a way of seeing the information the doctor gave me, that's a way of translating it into proper mathematical terms. The absolute risk is reduced from 12% to 8%. Percentage points is quite good to say, because the relative reduction is 1/3. So, now, should I take the tablets? Well, actually, out of 100 people have to take the tablets with their side effects for 10 years to prevent 4 heart attacks or strokes. That means that 25 people have to do it for 10 years for one of them to prevent 1 heart attack or stroke. Now, you know, whether you feel that's worthwhile, people feel it's worthwhile or not, well, apart from the crusty old professors, you don't have to worry about it yet, so that's fine. But different ways of presenting this have been shown to very strongly influence people's decisions, people's feelings. The other thing, of course, is that, well, there aren't 100 people like me. So another metaphor one can use, instead of 100 people like me, you could think of 100 ways things might turn out for me. There's 100 possible futures for me. Look, there's 100 possible futures for me. So there's 100 me's in the future. And 4 of them are actually delighted because they haven't had a heart attack or stroke because they've been taking their tablets every day. 8 of them are not so pleased. But the interesting thing is, of course, they shouldn't look delighted because if I take my tablets and I don't have a heart attack or stroke, I'll never know. Well, I wouldn't have had it anyway, whether I was a yellow one or a green one in 10 years' time. Maybe it was a complete waste of time. I'll never know what would have happened if I hadn't done something. The other way, it's also been shown to be important for people's feelings and judgments, whether you block these up or scatter them around. If I scatter them around, they're more difficult to count, but it gives a much bigger impression of unpredictability. You know, it's like throwing a dart. One of these is going to happen to me if I take my tablets. I throw the dart, which of them is going to happen? I don't know. Which of these possible features? Just don't know. And why I'm doing this is that we're experimenting now with methods like this to communicate risks to patients. This metaphor of possible futures is being increasingly used in public communications. You might start seeing it. The idea of, we build mathematical models, but they don't enable us to predict with certainty. So this is the result for Hurricane Irene, used in the national US news. These were different computer models producing different predictions for the path of the hurricane. So they put them all up and label the possible paths. I think that's a really powerful bit of communication. Because you usually see the sensitivity, the uncertainty, broadly you see it's probably going to go along there, there might be. There's a sort of feeling that these are equally likely, which I don't know if they are, but he was using this possible futures metaphor. Very powerful idea. And the point is that because, even though, is this sacrilege to say at an applied mathematics conference? We don't actually know exactly what the parameters are or what the models are. The Bank of England make these very explicit about their uncertainty. They produce these fan charts where they predict what growth will be over the next 3 years, and actually they say we haven't got a clue what growth will be. We think it'll be somewhere around here, and they don't produce a number. They refuse to give a number. It drives the journalists mad. They won't say we expect it to be 2% growth. They say it's going to be somewhere around there, and that's all they will. They will not give a number. And actually, there's probably a good reason, because this was November 2007. This is what... Oh, hang on. Oh, yeah. Because you've got to be ready for surprises. Because that's what actually... that's what actually happened. That was the projections, and that's what actually happened. Now, they were unapologetic about that. Now the reason is that that interval there only contains 90% of the possible futures. Only contains 90%. They've got 5% down here, and that 5% is essentially unallocated. So there's a 1 in 20 chance you haven't got a clue what's going to happen. You have absolutely no idea what's going to happen. And that was 1 in 20. It happened. So it was, they were unapologetic about it, which again says, must be ready for surprises. It's a warning for these. Now you've also got to be ready for bad maths. This is a pie chart from Fox News. This is a very good teaching example how not to construct a pie chart. They're supposed to add up to 100. So, yeah, I know, it's sad. So, you have to keep your eye open for these things. They pop up, and they're so beautiful when they do. Yeah. So the final thing I want to talk about, so I was going to talk about tragedy. I just want to talk about this instance of using maths in another sort of context, one where I was involved in this, and it was to do with this man. People don't recognise who this is? How should people know? Old people? I mean, the crusty old professors will remember. He's only got nothing to hide. He had quite a lot to hide. And he was a general practitioner, a nice family doctor, nice beard, and a sensible person. I've got nothing to hide. His only problem was that he murdered his patients in huge numbers. He murdered at least 200 of his patients. It's just outside Manchester, and probably quite a lot more. So each of these dots is an address of someone that he murdered. It was absolutely staggering. And so his practice was along there, great clusters, 6 in one street. And he did this for year after year after year. He was murdering his patients. And nobody could think it, again, let's be ready for surprises. Nobody could think it feasible that a doctor could be routinely murdering his patients. It just could not come into anyone's mind for a year, even though people were suspicious, thought this is a bit strange. Nobody could think it possible. So it's like the Bank of England. You've got to be ready for surprises. So I want to show we were brought in as statisticians to say, could he have been caught earlier? The public inquiry, the relatives of the people who murdered said, you couldn't have been caught earlier. So I want to show some of the analyses that we did. Now, this is a slightly strange plot, but it's got a lot of information in it. Each of these dots is someone he murdered. There's the data along here. Black are the women, pale these are the men, and these are the age. So, and these are the sort of histograms showing the distribution. So a lot of information. You probably haven't seen a graph before. You tend not to get that kind of thing in the newspapers, but actually it's got a huge amount of information. So did he tend to murder women or men? Women, yeah. Were they older or younger? Older. Do you think he changed his practice over time? Yeah. Look, it starts off with everybody was actually, everyone was over 65, so later on, moving younger. Yeah, exactly. Thank you. That was my next thing. Can you see is there a gap? Yeah. Why do you think there's a gap? And it's not because he had a holiday. We always say it. Why do you think there's a gap? Sorry? No, he wasn't investigated. No, that didn't happen until very later on. He was working, all this time, he was working with other GPs, the shared practice, like most GPs. But he thought that his colleagues were starting to suspect. So he left the practice and set up as a single-handed general practitioner. So there was a gap, and that's why he did it all. But once he'd set out as a single-handed general practitioner, there was absolutely nothing to stop him, no brakes. So he just carried on. And at the end of it, when he was arrested, he was murdered someone every 2 weeks on average. It was quite extraordinary. And he used to be, so what he used to do was, he'd visit. Okay, well actually, let's do another bit of stats here. This is, could he have been detected earlier? Well, we produced this plot based on data, which is the percent of deaths in each hour of the day. So this is when people die. And this shows for his other GPs, his colleagues. And people die throughout the whole day. You know, this is bumpy, but that's because the numbers aren't very big. And whether it's 8 o'clock at night or 10 in the morning or 5 in the morning, about the same number. People just die, you know, just there's no particular time of day. Except with Shipman. If we look at Shipman's patients, They all died between 2 and 3 in the afternoon. Not all, nearly all died between 2 and 3 in the afternoon. And that was got by someone going through all the death certificates and seeing what's the time of death. But nobody looked at it at the time. It was only done afterwards, after being called. So why do you think that all his patients died at 2 in the afternoon? Out in his rounds. And he said, out in his rounds. And yes, he used to do home visits. He was a very good GP. Very difficult to get a GP to do home visits. So he used to do home visits after lunch, and it was when the old people would be at home on their own, the families would be out, and he'd say, I'll just give you something to relieve your pain. And he injected them with diamorphine, essentially a heroin overdose. So they were it was very quiet and calm and peaceful, and they'd die right in front of him. And then he'd say, put their deaths down to natural causes. So it's extraordinary, it just hits you completely between the eyes. There's something really bizarre is happening. Nobody looked at the data. So the lesson from this is, unless you actually look at it, if anyone looks at it, nothing's going to happen. So the final thing we did was to look at the cumulative number of deaths, excess deaths, because you always expect some patients to die. But you can calculate what's called excess death, which is the observed number of deaths minus the expected number of deaths. And what happened is that it went up and up. This is for women, elderly men, just went up and up and up. These are more people dying than you'd expect to by chance alone. Now, by using, I won't go into the math, but by doing a whole lot of math with Poisson distributions, which is just the distribution of counts that you'd expect just by chance alone, you can put on thresholds, control thresholds, which tell you when you should ring an alarm bell. And for those of you doing A-level statistics, you know something about hypothesis testing. These are the type 1 and type 2 errors, 1 in 100,000, where these alarms are set, such that there should only be a 1 in 100,000 chance of falsely accusing someone of being a murderer, and there should only be a 1 in 100,000 chance of missing somebody who is a murderer. There's 2 types of errors. And with those things, you'd have caught in by 1984, where you'd only, not in 1985, when you'd only murdered about 40 people. So if people had been doing this, he would have been caught, no doubt about it. But nobody was doing it. And they started now, but it was a bit late. So what this showed is that statistics could have caught him, but only if someone had done it, had actually looked at it and done it. Without that, it's all pointless. Okay, so finally, about coincidence. My final coincidence story, if you saw this was in the paper last year, or the year before last year, is somebody bought a box of eggs and cracked them open, crack, and they all had double yolks. Every egg had double yolks. Amazing. So they were amazed. They went to the newspapers, it was in the Times, it was on Radio 4, and somebody said, oh, the man from the Egg Council said 1 in 1,000 eggs are double yolk, so the chance of 6 eggs, they're independent events, you multiply together the probabilities, 1 in 1,000, 1 in 1,000, blah, 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 and you want a million, not a trillion. What's wrong with this? Everything's wrong with this. This is the worst number that's ever appeared in the newspaper. And I think I've shown you, there have been some real crackers appear in the newspaper. This is definitely the worst one. If this was real, we eat 12 billion eggs a year, and even so, it would take 500 million years for an event like this to happen. Yeah, well back to the creation of the Earth. Oh, I wonder when the Earth was created. So this can't be right. This can't be right. It's completely wrong. You know, this number isn't right. Eggs aren't independent because you tend to get them from the same batch. But actually, it's wronger than all of that. What did I say about being ready for surprises? This is the crucial lesson from all of this. From Shipman, from the Bank of England, be ready for surprises. Because the next time I bought a box of eggs, they all had double yolks. That's in my kitchen, having a glass of wine. I don't know what this is going to do to my heart disease. I'm going to have a mother of all omelettes, and it's going to. So be ready for surprises. It's amazing. Is this a 1 in a trillion chance? No, it's because I went to Waitrose and I bought There's no chance of it whatsoever. This was not a random event. Which just goes to show something or other, but it goes to show that you shouldn't believe any numbers you read in newspapers. And maths is very important, but be ready for surprises. Okay, thank you very much indeed.
Okay, thank you very much. I think he enlightened and stimulated and have you. I think he's agreed to take questions. If we do allow questions, I think you'll have to repeat the questions for the people in the simulcast film, 0 people, or the likely outcome, having 0 people next door listening. So we will take 1 or 2 questions, if that's okay.
You mentioned a lot about newspaper reporters misinterpreting.
Yeah.
And you also mentioned that newspapers sometimes approach you. Have you ever been misinterpreted? You know, they approached you for comment, and then you said a thing, they reported that you said another thing.
Oh, I've had some terrible ones, which I went to press. I was threatening to go to the Press Complaints Commission. There's one where they had 12 hospitals who were operating on babies, and amazingly enough, half of all hospitals are worse than average. Can you believe it? Isn't that? Isn't it? It's a tragedy of mathematics that half of all hospitals are worse than average. So I was trying to explain this to them, and about you can look at the observed number of deaths minus the expected number of deaths, as we did with Ship. And in half the hospitals it's positive, they got more than you'd expect, and half got negative, they got less than expected. And I tried to explain to them, what they did then was take all the hospitals which had more deaths than you'd expect, in other words, the top half, added up all the observed minus expected, and said that these were all unnecessary deaths. Isn't that shocking? I mean, that's just like some minister who said, I won't be happy till everyone earns more than the average wage. So it's exactly the same non-numerate thinking.
I think just for me to say thank you again, David, for a fantastic lecture.